To introduce Dr. Lou Ziska. He recently joined Columbia University as Associate Professor of Environmental Health Sciences after more than 20 years at the USDA's Agricultural Research Service. So there he is, and welcome. Thank you.
Well, my thanks to the organizers for inviting me, although I must say that being the first speaker after lunch, when all the oxygen from your brain is going down to digest your food, isn't always the best time to talk about science, but we'll see what we can do. So I want to talk a little bit today about the nutritional aspect of rising carbon dioxide, and I want to try and put it in the context both of human physiology, but also in more of an environmental aspect with respect to pollinators as well. Now, we all recognize that carbon dioxide is going up in the atmosphere. Some of the latest numbers indicate that it's over 410 parts per million, certainly quite a change since I was born. How much more will it go up in the future? It depends on which model you believe. Some of the models, this green line is what I would call the everyone hold hands and drive a Prius line. So far, that doesn't seem to have materialized. We're more or less along the business as usual line where we're adding about 3 to 4 parts per million per year, another 80 years left in the current century, so another 240 to 300 parts per million to go. So I want to look at not so much the temperature aspect, which you've all been seeing this morning, really, and a number of excellent presentations. But what I want to talk about is the meme of CO2 is plant food. And I'm sure you've heard that meme, and you probably have just sort of dismissed it. But I want to give it a little more focus today. We know that plants are essential to life, and we know that plants require 4 basic resources from nature. They need light, they need nutrients, they need water, and of course, they need carbon dioxide. Well, about 90% of the 400,000 plus plant species do not have the optimal amount of CO2 that they need. So as more CO2 goes up, then plants should respond. And you can imagine that this has been a very much a selling point on behalf of certain industries. If you go to the ExxonMobil website, you'll see this slide. And on this slide is loblolly pine. And as you give loblolly pine more carbon dioxide, it grows more. Yay, loblolly pine. Wow, that's so great. That's wonderful. Wow. Now, if you're a forester, you recognize that the faster the tree grows, the weaker the wood, but somehow that didn't make it on the website. There's another aspect of this, though, that doesn't get a lot of attention, and that's this. When I change a resource in the environment that's going to affect 90% of all plant species, is every species going to respond the same way? And if it doesn't respond the same way, what are the ramifications of that? So let me give you an actual example. This is loblolly pine in a forest setting. And in this setting, we have large standpipes that are blowing carbon dioxide into the middle of the forest to see how the forest does, not just the individual tree. But here's the thing. In this forest is not just the tree species, but many of the other understory species that are also going to respond to carbon dioxide. And one of these understory species is a pernicious weed that some of you may have come into contact with, particularly if you're a dermatologist, and that's poison ivy. So how is poison ivy going to respond to rising levels of carbon dioxide? And as it turns out, poison ivy responds very well. It's a very good weed in terms of how it responds to carbon dioxide. In fact, it responds much more than loblolly pine. So what will weeds do in the future? I'm sorry, I keep saying weeds. I believe the current administration refers to them as alternative crops. So I don't want to confuse anyone, okay? So what happens with this in terms of global plant biology? What happens to this in terms of ecosystem function? The other thing I want to point out is not just a balance in terms of demographics, in terms of plant species, but also a chemical balance. Because when you look at where plants get their energy from, the carbon comes from the air, from carbon dioxide, yes. But the other elements come from the soil. The nitrogen, the phosphorus, the sulfur, the zinc, the iron, all of those are going to be impacted as well. And so what we're seeing is this imbalance occurring. The atmosphere is becoming carbon rich, but the soil isn't changing proportionally. So what does that do in terms of the balance? And in particular, one of the first things we wanted to find out about was nitrogen, the carbon to nitrogen balance, because nitrogen is a good proxy for protein. So when we look at rice, for obvious reasons, rice is something that I think 600 million people in the world each day consume more than 50% of their calories from rice, and over 2 billion people consume rice on a daily basis. When we look at these 8 different varieties of rice that are shown here, and we see that for the CO2 concentration that has already occurred, a decline in protein levels, that's pretty cool. That's pretty impactful. So let's look beyond that. Let's not just look at the protein. Let's look at what's going to happen for all the other integrated parts of nutrition. Now, this is another system similar to what I showed you for the Duke Forest. These are called FACE systems, by the way. FACE is an acronym for Free Air CO2 Enrichment. And you're simply putting out into the field the additional carbon dioxide that's blowing into the center of the ring. And within this ring, we had a number of rice varieties, japonicas, indicas, hybrids from much of Southeast Asia. And as with what we saw earlier for the CO2 concentration that had already occurred, here we're looking at a CO2 concentration of around 550 parts per million, which will certainly occur in the next 50 years. And so we're looking at all of the different varieties and all of the different declines overall with respect. There's hopefully some variation here. There is actually. But when we start looking at the average, we're seeing about a 10% decline overall in protein. And now let's go beyond that. Let's look at iron. Well, not only are we seeing a decline in nitrogen and protein, we're also seeing a decline in iron. We're seeing a similar decline in zinc. We're seeing a similar decline in other microelements that are part of the soil. So the stoichiometry of plants, of in particular one plant that at least 2 billion people every day rely on, is changing. What are the impacts of this nutritional change going to be? Well, beyond the nutritional parts of the micro elements that we were looking at, let's look at vitamins, right? We weren't able to do this for all of the lines. We were able to do it for 9 of the Chinese lines for vitamin B1, B2, B3, and B9. And you can see overall that there's pretty significant decline in these B vitamins across the board. And then we got this result, alpha tocopherol, or vitamin E, which went up. So we scratched our various body parts trying to figure out what the heck is going on here? Why is it going up for this, but going down for some of the B vitamins? And what we put together looks a little bit like this. If you look at the ratio of the molecular weight of the nitrogen to the molecular weight of the compound overall, what you find is that the more nitrogen there is in that compound, the more it's adversely affected by rising CO2. The change overall in the stoichiometry of what we're seeing with respect to carbon and other elements is basically reflected in the chemical structure of rice. So for alpha tocopherol, for example, there's no nitrogen. It's an all-carbon compound. It went up overall on average when you gave it more CO2. In contrast, when I look at vitamin B9, which is about 22% nitrogen by weight, it shows a decline. So that carbon to nitrogen ratio is not just something that is of interest theoretically, but it may be something that is also going to impact secondary compounds of plants overall. Now, it's not just crops. There is some interesting work that came out from Augustine and Blumenthal on pasture grasses for beef. And this is a 7-year study looking at percent nitrogen. And again, this was a face system. And they were looking at the effects this time of warming as well, of heaters that were put out. And what they found was that under ambient carbon dioxide, ambient temperatures, and ambient carbon dioxide and elevated temperatures, there was no effect on percent nitrogen. But overall, regardless of temperature, when they added elevated carbon dioxide, the percent nitrogen declined. And the end result of that was that it took, the cows themselves took longer to grow. They were stunted, basically. And it's not just a question in terms of the meat itself, didn't change in terms of composition, because the cows were smaller, so the ratio of the different elements didn't change. But of course, this has obvious ramifications if you happen to be a cattle rancher. So we've looked at it from the point of view of human food. And just to sort of add to this, there are a lot of data that are now available. And what you're finding is that for a number of basic crops, wheat, rice, potatoes, barley, etc., they're all showing, at least from a micronutrient and from a protein, a decline across the board. And what we're seeing, again, is this increase in carbon as the atmosphere becomes carbon rich, but this change in elements. The crops that are being affected are shown here. There is an exception, and that has to do with leguminous plants. Those that fix their own nitrogen do not seem to be affected. So peanuts, soybean, etc., seem to be maintaining nutritional integrity even with additional carbon dioxide. But these sorts of changes are going to have global impact in regard to nutritional profiles. So if rising CO2 will impact human food, what will it do in nature? And that's a pretty big question. So we're going to try and focus that down to looking specifically at pollinators. And pollinators, as you might imagine, are already under stress. They have colony collapse disorder. We have monocultures where their diet is being affected. Biofuels where corn is being grown over and over again. Corn pollen is their only source of food. Varroa mites, a new invasive species. Neonicotinoids that are being sprayed. All of these things are going to have an impact with respect to pollinator physiology. But can the change in CO2 also be something that's going to affect pollinator health? And so how do we do this? How do we go and look at how the recent change in carbon dioxide might have in fact impacted, let's say, the protein content of the pollen that the bees are using? How has it affected bee nutrition? So bees are pretty much two-source things. They have nectar, they have carbs. So in the case of rising CO2, we see that carbs are not going to be affected. Carbs may go up. And bees are very good at finding carbs. They have the little waggle dance that they do that, the bee tells their neighbor, oh yeah, right next to the 7-Eleven down on Fifth Avenue, you're going to find this sunflower plant. Boy, go check it out. But what they don't have a good sense for is pollen per se. Pollen provides the protein source for bees, and there are 10 essential amino acids in that protein source that bees need. So if carbon dioxide is affecting this particular protein source, how do we begin to assess that? That's a tough one. How do we do that? Well, we can look at, first of all, what are the last things that bees, quote unquote, see in the fall before they overwinter? And we looked at a number of different plant taxa, and what we found, to make a long story short, is that the distribution of these taxa vary. This is for an abandoned field. This is some work by Joan Edwards at Williams College. And what we found was that solidago was by far the overwhelming source of pollen for bees in the fall. So goldenrod was in fact the primary source of pollen for these bees. So we assume that anything that's going to affect the protein concentration of goldenrod pollen is going to have a significant effect with respect to bee health. So how do we find this? Well, we're going to try and do a two approach. We're going to try and do an historical approach and an evidence-based approach. So in terms of historical evidence, you have the Smithsonian Museum of Natural History. Great place, it's got dinosaurs, got the Hope Diamond. But way in the back in the basement, right next to the Ark of the Covenant, you will, okay, I made that last bit up, just so you know. But you'll find goldenrod samples that go back to the 1840s and beyond. And so we couldn't measure the protein specifically of the pollen, but we could look at the nitrogen content because it's an element and it's not going to change over time. So we did this, and we did this for lots of different sites within North America. We did a CHN elemental analysis of what we found. And then we went to look at experimental evidence. Now, this is before he retired, Wayne Polly was a USDA scientist at Temple, Texas. Really cool guy, but also this is a really cool setup. What he did, these things that look like Conestoga wagons, plastic Conestoga wagons, he's adding CO2 on one side, and as the CO2 moves through the Conestoga wagon, photosynthesis is removing carbon dioxide. So while this one Conestoga wagon might have 500 parts per million, the one at the end has pre-industrial CO2 of maybe 250, 300 parts per million. And fortunately for us, there was enough native Solidago growing along this transect that we began to assess it in real time. So in essence, this is the historical Smithsonian record. These are averages, I think, of 10 to 20 sites and locations. This is the estimated protein based on the nitrogen, and this is the carbon to nitrogen change in stoichiometry, going from CO2 values, pre-industrial, up to the values of about 5 years ago. And you can see so far, in fact, there's already been a significant impact in terms of the pollen protein concentration for Solidago of it's declined about 25%. And then if we look at it from the experimental point of view, we had fewer numbers to deal with, but the trends were overall about the same, the increase in C to N and a decrease in the pollen protein levels. It's in Proceedings of Royal Society if you want to find out more about it. Okay, right, so this isn't good. What do you do now, right? Well, it can easily enough to look at diversity of different diets around the world. People in Bangladesh, for example, about 70% of their calories come directly from rice. It's very limited in its diversity. But we are becoming the same way. How do we select for crops? Well, how many of you have eaten at McDonald's? You're among friends. It's okay, right? I personally like their fries. They're comfort food for me. I'm sorry. But their fries are actually derived from a single variety of potato, russet Burbank potato. So our diets are also becoming sort of less and less diverse over time, fewer things that we're relying on. So McDonald's buys 3.4 billion pounds of potatoes each year, and if you're a potato grower, guess which variety of potato you're going to grow, right? And this is how the current crop of production of potatoes in the United States is. We've reached a maximum, and it's now declining. So we need to diversify. How do we do this? What should we select for? Well, we have this very rapid change in carbon dioxide going on. And the question that I asked earlier when it came to loblolly pine and poison ivy is, do all plants respond the same way? Now I want to rephrase that question slightly. Do all varieties of crops respond the same way? And it turns out they don't. This is actually rice. Here we're looking at leaf area as a function of total biomass, but you can pick different metrics. And what we found was that at 300 parts per million, the CO2 that existed in the mid-20th century, is that when you look at cultivated and wild rice, they pretty much overlap each other. But as we've been increasing carbon dioxide, it's actually the wild or red rice that's responding. Breeders have no incentive to try and select for the most responsive CO2 lines. But if they do, this is a means by which you can actually exploit or take advantage of this additional CO2 in terms of making more yield. This is a way that you can begin to assess the genetic variability that exists there for things like nitrogen concentration or microelement analysis as a means to begin to adapt to these changes that we're starting to see. So this is just the seed yield. This is Clearfield. This is a typical variety that's grown throughout the southern United States, particularly in the Mississippi Delta. This is going again from recent CO2 changes, 300 to 400, here to here, and this is the wild line. Again, the wild line is increasing much more than the cultivated line because there is no incentive at the moment to see what these changes might be. Now, if you want to talk incentive, and this is kind of just for fun, is anybody on Google right now? Can you be on Google? Emily, or can you get on Google? I'm on it. Okay. When you get on Google, would you do something for me? Sure. On the search, would you search for carbon dioxide and marijuana? Sure. And then read me the first hit that you get.
No pun intended.
No pun intended.
How to use CO2 to increase yields in your marijuana crop.
How to use CO2 to increase yields in your marijuana crop. Wow. Cool. Dude, okay. There are opportunities here in terms of looking at it from a food security point of view. If literally millions of people are going hungry, why can't we begin to breed for lines of rice or wheat or barley that could exploit this additional CO2 in terms of making more seed yield? And just finally, this is some potato fields in Peru, and I wanted to sort of give you a different take on how they do agriculture. They grow the same variety, but around that variety, they plant wild potato. And then what they do is they look at the margins and they say, oh, well, this variety over here looks like it's got a really good taste. Oh, this variety over here, no, I don't think it's doing anything. Oh, wait, this variety over here is keeping this pest away. They are constantly evaluating what the genetic potential of potato is. And just out of curiosity, this is their production in terms of overall potato yields. So there's so many things here. I don't have the opportunity to talk about all the different interactions, but here are some of the ways in which plant biology can be impacted by climate and what it means for public health. We have changes in fire frequency. If CO2 is plant food, how does it change that basic combustibility of the plants that are being set on fire? Does it increase it? Does it decrease it? Does it change? We know that things like kudzu produce volatile organic compounds. Kudzu grows in disturbed areas by cities. How does it contribute to the overall ozone levels? How will it be affected by rising CO2 and changes in temperature? Contact dermatitis. I didn't mention this, but in fact, the poison ivy that was grown under high CO2 produces a more virulent form of erythritol, the oil that causes contact dermatitis. Narcotic intensification. How much money do we spend each year in terms of trying to eradicate coca? Well, if climate changes, where is coca going to be growing in the future? Have we included that information into our current efforts? Food allergies. If CO2 affects protein, how does it affect food allergies? Looking at food safety. Hey, more warmer temperatures. What happens post-harvest in terms of our vulnerabilities to things like salmonella, clostridium, changes in pesticide use, herbarium, or herbicides. This is a study that we did where we sprayed this with the glyphosate at the recommended dosage. This was under ambient CO2. Here's under elevated CO2, sprayed with the same dosage, got zero control. So if we increase pesticide use, what are the impacts of that going to be in terms of public health? There's so much going on here that I don't really have time, unfortunately, to go into. But I just want to acknowledge that when you hear that phrase, CO2 is plant food, give it a second thought. Think about what that really means in terms of not just human health, but in terms of our environment overall. So we think that the potential for basic and applied research and the impacts of potential research is enormous. It's enormous. There's so many opportunities that are out there. Now I know that we're, of course, in our own little silos. We're reductionist in nature, that's who we are. We have our own silo. I'm sorry, I think the current administrative term is cylinders of excellence, so I don't want to confuse you. So within that, we want to be able to try and do what we do best, but to hold hands and work together. Because when you start looking at climate change effects on health, it's not a one-off. There are lots of things that are going on, lots of things that we can focus on. So if you have any additional questions or want to contact me, that's my new email. I've been at Columbia now for about 5 months. Very, very happy to be there. I'm happy to be at a place where climate change is not considered a Chinese hoax. So thank you all very much for listening.
Thank you very much. I have one question here, and then we can get a few from the audience. I don't have any more cards. We can bring them up. You mentioned it, but what can we do to prevent the decline in the nutritional value of crops? You mentioned diversification, but can you elaborate a bit more?
Sure. What happens is that seed companies and major businesses tend to rely on sort of a very narrow subset of genes. We have this assembly line approach when it comes to food, and I think that hurts us in terms of having that nutritional adequacy. The other thing that needs to be kept in mind is diversity of diet. It's great, for example, if you want to come up with GMOs like golden rice that produce more vitamin A, but it's equally good to try and see whether or not you can plant sweet potatoes next to the rice as a means to diversify both the diet, but also to provide the vitamin A that's necessary.
Okay, do we have any other questions? All right, thank you so much for
Thank
your
you.
presentation.